Do we finish chapter 7? No, we probably need one more lecture. The topics are very deep, so we need to spend enough time to talk about them. You can give it a quick read, but...
Yeah, the textbook is very complicated.
Is it?
Well, it's just like hard. There's a lot of information.
But it's intentional because then there's another chapter, chapter 9, that we go back and talk about. I'll point out what we will cover again. Okay, so we're going to start. We continue our lecture on vector spaces, chapter 7. This is the second lecture on part 1 of vector spaces. Our learning objectives have not changed. We still want to learn about vector spaces, understand linear combinations, linear independence, and what it takes for a solution of a rectangular system of equations, not necessarily square, to be unique. That's what we're going to talk about today. And LDLT is a topic that we will talk about it in the next lecture. Now I start with motivating an equation that you will see today again and again. We want to know why we are looking to the solutions of that equation. So we have a matrix equation AX equals B. We understand that something such as X bar is the solution of this matrix equation if it satisfies the equation. That means that if A is multiplied by X bar minus B, it gives us exactly 0. The solution means it gives us exactly 0. Now suppose there is an alpha vector similar to X bar, same dimension, but it's another vector. We call it alpha. It's not 0. It's not 0, that means not all of its entries are 0, right? This is just a lazy way of saying that it's not a vector of all zeros. And suppose that this is a solution of A times alpha equals 0. Same A matrix. There's no problem with writing that, right? We're just imagining that there is an alpha, that if we multiply A by alpha will give us 0. We don't know what alpha, what a specific value, but we can imagine there might be such a vector. What happens is that if we sum up these two equations, right, we can add them up. We get AX plus A alpha equals B, right, plus 0, which we can, using the properties of vector spaces we talked about, this can be factored into A. Sorry, this is X bar plus alpha. And we can always move B to the other side, minus B equals to 0. Now, is this concerning or it's okay? It is concerning. So you look concerned, you're not? It is a little concerning, right? Because when we say the solution is unique, when we talked about it, we said that there's only one of them. Now, if there is an alpha, that if you multiply A matrix multiplication A times vector alpha, it will result in 0. Now, there's also the case that x bar plus alpha is also the solution of the system, because it also satisfies that A times x bar plus alpha minus B equals to 0. Now, that violates the fact that we say x bar is a unique solution of this system of linear equation. So it is not. If there is an alpha, right, then the solution is not unique, because any solution plus that alpha is also a solution. The set of solution will get bigger. It's not unique. Which, by the way, if alpha 0 is always a solution of this system, right? Obviously, if alpha is 0, this is always true. And in fact, if it's 0, x bar plus 0 is x bar. So that's not concerning. Alpha 0 is called the trivial solution of this system. We are not concerned about that. That's always true. And 0, you know, that's the origin. That means we're not shifting the solution to different vector and point in the space, and yet it satisfies the equation still. That's not the case if it's 0. Okay, so we conclude that x bar plus alpha must be a solution too. Now, this is concerning because then we want to talk about uniqueness of a solution. That's important to us. So because of that, we are motivated to study this matrix equation, A times alpha equals 0. So the reason the right-hand side is 0 because of it's the consequence of what we just saw. Because we can add them up without changing the right-hand side, it changes the solution. So this type of equation, A times alpha equals 0, is called homogeneous equation because the right-hand side is 0. And alpha, if there is an alpha that is non-zero, it's the solution to the homogeneous system of equations. Just a side note, if it's not 0, it's B, like this, then x bar is called a particular or a specific solution to the system. Because for different values of B, you get different possible solution if it exists. So that's specific to what is the right-hand side. And the solution of the system overall is always the sum of, we just saw that, sum of the solution to the homogeneous system and the specific solution, because the homogeneous has a 0 on the right-hand side. If you take a course in differential equations, they will talk about these ideas, but they come from more basic topics in linear algebra. Okay, so we have every reason to study this equation. And we're looking for alphas that are obviously not 0. 0 is, we're not concerned about that, as I said. So any alpha that is not 0 and satisfies A times alpha equals 0, we call it a non-trivial solution, because it's not obvious. 0 is an obvious solution. So this is our journey, and then we're going to connect it to different topics of invertibility of the matrix and linear independence of vectors, and they all mean the same thing. In the end, we see that how they are all connected. Okay, to start, now we have the motivation. We're going to build up to the point that we can come up with a set of rules that we can check whether we have a unique solution or not. But we need some new ideas. We need to define a few things. The first one is the concept of linear combinations. Now consider AX equals B, a matrix equation. We already know we can write A. Now A is n by m, is rectangular, right? It's not a square. And X is m by 1. So that when we multiply them, it makes sense. Because we can multiply an n by m by 1 vector. And what will be the result if I do? So what's the size of B? Yeah, so if A is n by m and X is m by 1, from matrix multiplication, we know that B must be n by 1. Because we sum over this common number of columns of the first one and the number of rows of the second one. Okay, that's correct. In chat, see n by 1. Now that's strange because this is a rectangular system, it's not a square. So the matrix is not a square matrix. So we need to be careful. It makes sense to define that equation. Now using our second way of multiplying matrices, we know that we can write A times X as sum of its columns multiplied by rows of X, and rows of X are just are scalar variables or ultimately some numbers. We've seen this before. And from properties of vector spaces, we talked last time that we can always move each X to the other side. That's not a problem. So this is just the second way of multiplying matrices. I'm decomposing the matrix into columns times rows of the vector. Now, just purely for the psychological reason, not to think about X as a variable, let's replace it with each xi, we're going to replace it with alpha I. We're not changing anything, but we want to think about alpha as a specific numeric vector that we want to calculate. Whereas X is more, generally we use it as a notation for a variable. So it's a common notation that people use. But in principle, we're not changing anything. We could just use X. So A times alpha is alpha 1 times first column of A, right? First column. Alpha 2 times second column of A, all the way, alpha m times how many columns? M columns. Should be A. Okay? Now, we are ready to define the linear combination. The linear combination is just sum of scalars times vectors. So it is exactly what we saw when we multiply a matrix by a vector. Anything in this type, alpha 1 times a vector plus alpha 2 times another vector, and you sum them up, this is called a linear combination of columns of A. Okay? Is it clear to everybody? Do you have any questions so far? Just feel free to interrupt if any part of it is not clear. So we call this a linear combination of some column vectors. Now, when we do that, we go back to our system of linear equations, and if we use alpha instead of x, we have A times alpha equals B. We can, of course, write it B equals A times alpha. This should not change anything. But when we do that, we start thinking about B differently. Not just the right-hand side of the equation to hold the equality. But now we have this fact that if we write A times alpha as a linear combination of columns of A in the right-hand side, and given that this equality should hold if alpha is a solution, right? Then we conclude that B is, in fact, can be expressed as a linear combination of the columns of A. So the right-hand side of the equation is a linear combination of the columns of A. Okay, this is just, we haven't created anything new. This is just a realization that if we talk about linear combination as just weighted sum of columns of the matrix, then B is the linear combination of columns of A. Okay, so this is just another way of thinking about B. So by multiplying columns of A and adding them up with different real numbers and adding them up, we should be able to produce B, right? B is not arbitrary. B cannot be any vector if we want alpha to be solution of this AX equals B. We should be able to produce B by multiplying columns of the matrix A and summing them up. Any alpha that allows us to do that is a valid solution. And if we cannot produce B by that alpha is not the solution of that system, because it just doesn't satisfy this equality with this new realization. Okay, that's the importance of it. Now, we talked about drawing these columns as vectors in the space last time. This goes back to that visualization as well, that we should be able to produce B by taking those directions vectors and weighting them differently and adding them up to produce another vector called B. If we cannot do that, this equation does not hold, right? So you can think about it as, visually you can imagine that's what we're doing. Which raises the question that, well, can we always do this? Let's just think about that examples that we gave for two vectors, and they were parallel, right? And if you're in a 2D plane, and two columns that we had in our examples, one is 2 times of the other one, both are pointing to the same direction. Is it possible for us to produce another direction in the 2D plane by just multiplying and summing them up? So what I'm talking about is that I have one column like this, and I have another column like this, right? A 2 by 2 matrix. A2. And I'd like to say this is my B, right? Can I write B equals alpha 1 times A1 plus alpha 2 A2? Whatever you want to pick. Alpha can be negative, positive, right? Any number. Is it possible? Not sure. You're not sure if it's possible or not. Now, if you're not sure about this, you're definitely not sure about something that you cannot visualize, right? So I let you think about this. Both columns are pointing to the same direction. Can I weight them differently, add them up to produce another direction that is not along that direction? Excellent. So if you're saying that if I multiply a vector by a scalar, there is no way I can change the direction of that. I can just change the length of the vector. It's just the magnitude of it. I can stretch it. I can maybe multiply by negative value, right? Maybe pointing to the opposite direction. But it's never going to change its direction. So it's not possible, right? It's not possible to have a solution that is, this vector B is pointing to the completely different equation. That goes back that if we put these two columns in a matrix and take the determinant is 0. This will be a nice 2 by 2 matrix. Easy to calculate its determinant. Now this is the root of the problem, and it's just not possible to visualize if we're dealing with high-dimensional spaces. We need something that is systematically scalable, and then it gives us some set of tools for verification. We can quickly verify using computer whether this is the solution is unique or not. Now, this has very important physical implications in a lot of applications in control, in estimation theory. This could mean that your physical system has a mode of operation that is just not observable. And that can be very dangerous because when you observe it, it's too late. It's exploded already. You're not going to be able to observe that. You take a course in control, linear systems, they talk about these ideas. And you'll see that they will use just everything that you learn here, these tools of linear algebra, but it's in the context of more application and engineering. And in chapter 9, we will explore more of these ideas. Okay, so now we will keep expanding our imagination of how we're looking at just a simple equation that A times X or alpha equals B. We're giving it very different meanings, thinking about directions, linear combination of columns of A, and the fact that B must be a linear combination of those columns. Otherwise, the equality will not hold. Okay? Let's formalize the linear combination in Rn. the n-dimensional Euclidean space. Now, a vector that belongs to the set Rn is a linear combination of a bunch of vectors, m different vectors that form a subset of Rn. If there exist real numbers, alpha 1 to alpha m, such that we can write V to be a linear combination of those vectors. So each vector's length is n, because it's in Rn. We have m of those vectors. We weight them and sum them up. And if this holds, then V is a linear combination of those vectors. Now, if you might not be familiar with this notation, that what I mean with this notation, this is subset. When we say A is a subset of B, we mean that B is a bigger set that includes A or contains A. For example, imagine a set of 3 numbers, very simple example, 1, 2, 3. 1 and 2 is a subset of that. Now, Rn is huge. It's all the vectors, n by 1, right, that you can create with changing each of the entries with real numbers. There are infinite number of them. We can't even count. So that's a very tiny subset of Rn. But also depends, m is less than n, bigger than a, right? In chapter 9, again, we're going to talk about span. How much of the space this subset will cover? We don't know. Like, Rn is huge. Can I cover the whole space with this, or it covers a part of it? And then we talk about the idea of span, and that will tell us, make it clear that how much of the space this will cover. Okay, so let's look into some examples. Is V a linear combination of U1 and U2? This is V, U1, U2. Or maybe I write it. Can we say V is a linear combination of U1 and U2? You want to give it a shot? From this side? You guys been active? By the way, have you noticed the color of my shirt is inversely proportional to the difficulty of the lecture? When I wear dark, those are nice lectures. I have a very nice white shirt, ironed and ready in the closet for future lectures. Can't wait to wear that. I'm kidding, it's wrinkle-free, it's always ready. I thought you raised your hand.
Yeah, I'll give it a shot. Thanks.
Yeah, go ahead.
So, I mean, basically you're adding the 6 and the -9 to get -3, so that one works for the top row. And then you're doing 4 plus -9, which is -5, so that works. And then 2 plus -9, which is -7, so that works. Like just kind of looking at it like on a row by row basis.
Okay, so your idea is that, I mean, this is given, but let's verify if 2 sides are the same, right? Yeah. Okay, that's a good idea. So we say V equals 6, 4, 1, minus 9, 9, 9, minus 3. Help me out. Minus 5.
There should be a 2. Yeah.
Oh, yeah. The rest of my slide would be wrong. Okay. So the equality holds, and I mean, we didn't trust that the question is giving us the equality. That's fair. So V by construction is weighted sum of U1 and U2. So you can say that it is a linear combination of those, right? So it's like a forward way of checking it because it's given to us. Not very difficult. So that means that you do not need to store information about V if I tell you what are the alphas, right? What is 2 minus 9, and then U1, U2. You can always reproduce V by just knowing that. Now, another example is the vector V, a linear combination of U1 and U2. Is this similar to the previous example? Is it? It is, but I'm not giving you the coefficients, alphas. That changes everything. There's nothing to verify because you don't know what's alpha. Can't be anything. Makes it very difficult because now you need to find out if there exists a vector alpha that will do that for you, to make V a linear combination of U1 and U2. And you're stuck because we need a way of obviously calculating alphas. So we do not know how to solve it yet, or at least verifying. So there are two ideas. One idea is that you go ahead and solve for those alphas, right? Specifically, what is that vector that's not 0? Here obviously shouldn't be 0, and will produce V. And the other idea is that you come up with an idea, with a trick that you can verify. You can tell me whether it's a linear combination or not without actually solving for alpha. So a lot of times we have, in practice, these two powerful ideas that not always you need to solve the problem to verify something. And verification tools are very important for checking correctness or issuing a certificate of, for example, correctness for a method or algorithm. So much of today is about verification. We see some examples and we can solve a homogeneous system of equations. That's not a problem. But we are more interested into the verification part of the work. Okay, we need to develop a way to check if a vector is or is not a linear combination of other vectors. From previous examples, we realized that we need that, but why do we need that? We might have forgot why. You remember?
Well, I think, just to save us a lot of time, right, instead of having solve each individual, solve the system.
For solving the system, there's existence of the solution, right? Because we said that the equation A x equals b has a solution if and only if b can be written as a linear combination of its columns. Now, if we have a tool to verify b in general, if a vector is a linear combination of other vectors, or b is a linear combination of columns of A, then that will help us to study the existence of the solution and ultimately uniqueness of the solution as well. Okay, so we recognize that we need some more tools but also we are motivated why we need those. So that's important. So that brings us to formally discussing what is the condition for a set of vectors to be linearly independent. Now the set of vectors are, we assume we have m vectors and they're part of Rn. They're linearly dependent if you can find a set of coefficients, alpha values, not all of them zeros, right? Because we already know that's a trivial solution. You find a set of alphas, not all of them zeros, and somehow you can combine them with all the vectors v1 and v2, and that will give you 0, okay? So if you can find such alpha values, to scale each v, add them up, say it formally, calculating a linear combination of the set v, and that will give you 0. Then we call this set of vector here to be linearly dependent. Does that make sense to you? Why it's like that? Because if one of them is a linear combination of the other ones, we can always find some values to balance whatever the rest of the set are, right? Make it 0. That's why. If all of these vectors are in a way that are independent, then we cannot cancel, let's say, m minus one of them with the one that is the weighted sum of them. That's basically the idea here. Now let's think about the opposite. The set of vectors of v1, v2, vm are linearly independent if the only vector alpha that will yield this condition is the 0 vector. In other words, the only solution is the trivial solution, alpha equals 0. So if you cannot find any alpha to non-zero alpha to generate this, to satisfy this constraint here, and the alpha 0 is the only condition, then these are linearly independent. Independent. Okay? We just said it in two different ways. What is the condition for them to be dependent, and what's the opposite of it to make them independent? Maybe we can pause for a moment, see if you have questions. See people in the first row are meditating, practicing mindfulness. Which makes me think that too easy or too hard. It cannot be the middle ground. Okay, let me know if you want me to go back. I'm going to move to a concise definition for linear independence. So the condition implies that the linear combination of a set of vectors v1, v2, and vm equals 0. These vectors are linearly independent if and only if the vector that satisfies this constraint is the vector alpha equals 0. That's the concrete definition of linear independence. It's very helpful probably to write two-dimensional vectors and play with this idea, see what it implies. Or three vectors with lower dimensional examples. Try to make sense of it. If we had an example, we can go back to that example as well. Okay, so we also note that another realization, that constraint, it felt like it came out of nowhere, but it's in fact, it's the same as saying it's a linear combination, so it's A times alpha, right? We already know that this is scalars times vectors, and summing them up is actually the second way of multiplying a matrix times a vector alpha. So it was actually the same thing as our homogeneous equation. So we're not actually talking about anything new. We say the columns of A are linearly independent if the only solution to this equation is alpha equals 0. That's what we're saying. Which goes back to the initial motivation that because if it's not, then the solution is not unique because we can add it to any other specific solution of the system. Okay, so we recognize that if we are asked such a question that tell me if this set of vectors are linearly independent, we start thinking about a homogeneous system of linear equations. We arrange these vectors into columns of a matrix A, and we put all the alpha values into a column vector, and then we immediately form A times alpha equals 0. So that helps us to collect them into something compact and familiar. Let's look into an example. By applying the definition, determine if the set of vectors v1, v2, and v3 is linearly independent or dependent. Where should we start? Well, there's no B. We are just asking if the set of vector is linear independent.
Oh, okay, sorry.
Yeah. That's also true, but here there's no discussion around B yet.
Yeah, sorry.
Yeah. Well, you don't have to apologize. It's good to have. That's a very good point because let's not talk about B. Yeah.
You can put all three of those columns together to create your A matrix, and then you would say that like that matrix times alpha is equal to 0.
Yeah, that's a good idea. I mean, let's turn it into a familiar form. How about we form A and the homogeneous system of equations, see where it takes us. And, okay, so the definition first is this, right? The definition of linear independence is that alpha 1 times v1 plus alpha 2 times v2 plus alpha 3 times v3 must be equal to 0. That's the definition. Now we arrange the linear combination of these vectors into a matrix equation. And to do that, we can form matrix A by adding putting these vectors into its columns. So we get our 3 by 3 matrix in this case. And we form a vector alpha, which includes alpha 1, alpha 2, alpha 3. So that's just our constraint here, right? We're putting it in a matrix form. Okay. Now, we wish to find the non-trivial solution to this system of equations. A times alpha equals 0. Now, this is a little different because even if A is a square and invertible, it's not like you can invert it and multiply it by the other side because that will just give you 0, right? Which we'll see in the end if it's invertible. That's the only solution, but in general, this is a little trickier than a usual system of equations. But in this example, it's fortunately already in an upper triangular form. So A is an upper triangular matrix, so we can use back substitution. Now, by just looking at this equation, tell me what are the possibilities. We can, based on the back substitution, we start thinking from the most bottom row, right? Look at the bottom row and then make your way up to the first row. Then, what are the possibilities that the equality holds? We are first think about this part. Well, you are recognizing that alpha 3 must be 0. There's no way minus 1 times alpha 3 equals 0 has a solution other than 0, right? This is just a scalar. There's no other possibility. So we conclude that alpha 3 must be 0. Now, if that's 0, we look at the second row. The second row will tell us 7 times alpha 2 plus 1 times alpha 3 is 0. This is telling us 7 times alpha 2 equals 0. Again, the same condition. This is just a scalar. Alpha 2 must be 0. First row, we are arriving at the same situation. Alpha 1 must be 0. So in fact, we just arrived at the situation that the only logical explanation here is that alpha must be 0. What does it tell us? And the question was asking, tell me if V1, V2, and V3 are linearly independent. And our conclusion was that if we write down the constraint, the only vector that satisfies this constraint here, the definition of linear independence, is 0. Alpha equals 0. What does it mean? So it means the only solution is the trivial solution that we talked about it. That does not tell us anything. It does tell us something, that they are linearly independent. It doesn't tell us anything in the sense that from the beginning we know that's the solution. But we just verified that that's the only solution. So when alpha equals 0 is the only solution, then these vectors are linearly independent.
I assume we're eventually going to get to learn like the importance of being linearly independent or linearly dependent, right? Like how that helps us with anything.
Can you repeat it? We eventually learn.
Yeah, are we going to eventually learn like why it's helpful to know if something's linearly independent or linearly dependent?
Yeah, are we going to learn eventually why it's helpful to know a set of vectors are linearly independent or dependent? Yes, because that goes back to the existence and uniqueness of the solution of the set of equation ax equals b. That's our motivation. Okay? For a rectangular system of equations. For a square, nice square system of equations, we already know the determinant of a must be non-zero. But what about a rectangular system of equations? The determinant is only defined for a square system of equations. So we are building up to that point.
So if the system is linearly independent, does that mean that it will have a linear combination solution? Is that kind of, because like the earlier slides were saying like we need to find a way to quickly.
Not necessarily. So you're saying that if the columns of A are linearly independent, can we say the system of equation A times x equals B has a solution? And my answer is that that depends what is B. Because for certain B right-hand side, that's true. Not all vector on the right-hand side will satisfy that because B must be a linear combination. We will have a condition on that too eventually, right? So both the idea of being linearly independent and being dependent, we need both of them because on one side, we want columns of A to be linearly independent so that we can explore all the directions in the space, right? As far as we're concerned about that matrix. But of course, that depends on the space the problem is defined on. For B, we want it to be dependent so that we can produce that vector that is on the right-hand side. So we're going to need both of them eventually. Which now we arrive at a pro tip to calculate linear independence. This is too painful to write everything and derive alpha. That was a nice upper triangular system. It could be so much worse. You'll see some of them in your homeworks. Keep it nice and beautiful in slides. Okay, so let's make it as more systematic. We can just use matrix multiplication and computer to verify that. So a good point in chat, Professor Grizel is pointing out that independent vectors means that no redundancy in the collection of vectors, right? We don't want redundant vectors. That means if one of them is a mix of the other ones, we don't want that. We want to detect that. We want these vectors to be independent direction in the space. If there's any condition, we can produce one of them by mixing the other ones. We want to be able to detect that because that has consequences for solving the system. I think this is a very deep insight into thinking about a system of linear equations, because the moment you think about columns of matrices, direction in the space, linear combination of them, that's a very powerful image, and by no means it's simple. A lot of people don't have that imagination. I want you to think about it. That's a very powerful image to build in your mind.
I have a follow-up question to that. So essentially, have a 3 by 3, or sorry, like three column vectors that are of length 3. So like each one is a 3-dimensional vector essentially. So essentially, like what you're doing by checking, doing all of this, is saying that if you like plot all 3 of these 3-dimensional vectors, there is no way for you to get one of them from the other by applying like a scalar to it, or is it, and that's specifically being scalar, right? Because obviously you could.
Yes. So the question is that if I have 3 vectors in 3 dimensions, are we talking about the condition that I cannot produce one, excuse me, one of them by a linear combination of the other 2? That's exactly what we're talking about. Which that constraint, that linear combinations of them equal to 0, it gives us all of them, because otherwise you have to write, for every of them you need to write this condition, right? But then if you can sum all of them, that will give you one constraint. Okay? And then you can imagine this is my 3D space, right? Imagine I have a vector like this. Now I have another vector like this, right? Now these 2 vectors, regardless of are in parallel with any of the axes or not, they will form a plane. I guess we all agree that I have 2 lines, 2 vectors. Imagine a plane that is including both of them, right? Now this is a 3D space. I need a direction that points out outside of this plane. To be able to move to any point in this 3D space, I need a direction that is not on this plane, right? If my third vector, if the third vector is a linear combination of these 2 vectors, then it must lie on the plane, right? And that's, let's say this is V3. And that's bad, because no matter how much I try, I will lie under this plane. There is no way I can escape and go to another point like here. Maybe I want to point out, maybe the B that you're after is here, right? There is no way you can produce this B. Now this is nice to look at it, and it's very helpful, but in a 10-dimensional space, in a 100-dimensional space, things can go wrong, and then we need to be able to detect this, okay? Does this picture help to answer your question? I think the geometric intuition here is very helpful.
But also, like, so then wouldn't B3 in this case be like the B of our AX is equal to B equation?
Well, because it's 3 by 3, we're talking about V1, V2, V3.
But there's no alpha 3 though.
Times, well, we could have alpha 3 here. And then you can divide alpha 1 and alpha 2 by alpha 3. As long as it's not 0.
So if we prove that they're linearly dependent, then that equation holds true, or if they're linearly independent.
Now, if the only values that this equality holds is that alpha 1, alpha 2, alpha 3 are zeros, right? Then that was our definition. Then we mean that V must be somewhere else. It's not a linear combination of V1 and V2. These 3 vectors are independent, which implies that we can explore this 3D space by just mixing them up and move. That's why we have 3 axes, right? X, Y, Z. They don't have to be orthogonal, perpendicular to each other. We can still mix 3 independent directions to move in the space. So that's really what we're talking about. This is the geometry of it. Again, it's not possible to visualize when we go to higher dimensions. And we want you to not get stuck into thinking about 2D and 3D space. So we need to add these abstraction and definitions. Because if we put too much emphasis on these 2D and 3D spaces, you might miss out on more abstract ideas of high dimensional spaces. But this was very helpful. I like this image. Now, how about we multiply both sides of this equation by A transpose? Now, in principle, we can multiply both sides from left by whatever matrix that makes sense, as long as the dimension is correct, right? That's not a problem. But A transpose is very special. Why? Because when we do that, of course, we get A transpose times A times alpha equals to 0, right? Because the right-hand side is 0. A transpose is special in that gives us square matrix. So A is n by m. A transpose is you take the rows and put them in columns, right? It changes the size of the matrix. We get m by n matrix. And A is n by m. So the whole thing is, if you're comfortable, you can define it as a new matrix. Or you can just think about it the way we write it. Now this H is m by m. So A transpose A will give you just another matrix. And that will be a square matrix, always. So it sounds like we can convert a rectangular system of equations to a square system by multiplying from left by A transpose. Okay. Now why, if we multiply by A transpose, this is still true, why do we have a reason to believe that it will not change the problem? And the logic behind it, that it's explained in the book as well, that if you have a vector of zeros, right, n by 1, y transpose y, which will give you a scalar, right? Because y transpose is n by 1 by n. This is n by 1. This is 1 by 1. Now, this is true that if y transpose y is 0, then y must be 0. Okay? Because y transpose y is y1 squared plus y2 squared plus all the way yn squared. So sum of a squared of a bunch of variables, right, is 0. Then all of them must be 0. Because they cannot be negative, right? They're all positive. And sum of them is 0, then all of them must be zeros. Okay, so now, so if y transpose y is 0, then y itself is 0. Now let's define A times alpha to be just another vector, just like y. And I'm going to try to multiply A times alpha by A transpose from left. Then I'm going to multiply from left by alpha transpose. Because it makes sense, the dimension of these terms allows me to do that. Now I recognize that alpha transpose times A transpose is just A times alpha transpose. If you remember, A times B transpose was B transpose times A transpose. Now I recognize that, so I put them here, and A times alpha was Y, right? So Y transpose times Y equals 0. Therefore, Y itself must be 0, and Y is A times alpha. Now we started from A times alpha equals 0. We did everything that we wanted, and then we circled back to the first conclusion. So from the logical point of view, we started from one point, we tried different things, and then we moved back to the first point. Then that makes all of them equivalent. They're all the same, because wherever we are, we can just continue and go. It's a circle, right? You can always continue and go back to the point you want. I have a condition 1, 2, 3, 4, 5, 6, right? I start here to this point, right? To this point, and then all the way to this point. So at any time, I can just move on this circle to be in whatever form I want. So all of them must be equivalent. All right, so we recognize that, and logically, we go from A to B to C to D and A again. So then we can go back and forth. Now I'll let you think about this, but again, the reason is that because this holds. So if A times alpha equals 0, then A transpose times A times alpha must be also equal to 0. Is this useful? No? Anybody thinks this is useless? You won't be penalized if you say that. Now, why did we do this? Because this was a square, right? This was A was n by m, but this is m by m. We turned our system of a rectangular system of linear equations to an equivalent system of equations that is a square. Now, if you remember, for a square system of linear equations, we could easily check using the determinant to know whether the solution exists and if it's unique. So it is very useful, in fact, that it generalizes whatever we learned early on in the course to a rectangular system of equations. So to summarize, consider the vectors in Rn, v1, v2, all the way to vm. Let's arrange them into columns of a matrix such as A. And when we do that, the following statements are equivalent. You can say the set of vectors, you see this in math a lot. They say the following are equivalent, that means all of them mean the same thing. You can conclude one from the other one. The following statements are equivalent. That means the set of vectors v1, v2, and vm is linearly independent. Or you can say the M by M matrix A transpose times A is invertible. Or you can say the determinant of A transpose times A is non-zero, which you know these two already, right? If it's invertible, the determinant must be non-zero. But before today, we weren't aware of this. Or you can say that if you calculate the LU factorization of A transpose A as a new matrix, which must be P, a permutation matrix, times A transpose times A equals LU. This is a LU factorization of A transpose times A. Then the upper M by M upper triangular matrix U has no zeros on its diagonal if the set of vectors is linearly independent. Okay, so all of them, they mean the same thing. So we could turn a new problem of knowing if a set of vectors are linear independent or not, right, into some conditions that we are familiar with them. Now, why the last one is true? What happens if U has zeros on its diagonal?
And the matrix has either no solutions or an infinite amount of solutions, and then that means that there's another solution besides all zeros, which means it's not linearly, or which would mean it's not linearly independent. If there were zeros.
The fastest answer is determinant, right?
Oh, yeah.
Yeah? To say the same thing in just a few words, you can say that because if you remember, the determinant of a triangular matrix was just the product of its diagonal, right? So if U, which is an upper triangular matrix, has any zero on its diagonal, even 1 zeros, right? The determinant will be zeros. And the determinant of LU is, of course, determinant of, we talked about this, that determinant of the product of two matrices is the product of their determinants. So if this is 0, this makes the whole thing 0. Now, if the whole thing is 0, it violates this condition, which violates this condition. Then it's not invertible, which violates this condition. They're not linearly independent. So the last one is particularly interesting because it decomposes everything and we can see what's going on. And the next time when we talk about LDLT factorization, we separate vectors that are dependent explicitly through the factorization of the matrix. So let's look into an example. By applying the definition, determine if the vectors v1, v2, and v3 are linearly independent or dependent. Now this is a 4x1 vector, okay? So what we can do, we can form matrix A. This is a 4x3 matrix. Of course, we cannot take the determinant to know if it's non-zero or not. We form A transpose A in Julia. You don't have to do it by hand. We get a 3 by 3 matrix. Again, we use Julia to calculate the LU factorization. That will give us P permutation matrix, L, and U. Now, we already see that U has a 0 on its diagonal. So we already know that A transpose A, its determinant is 0. You could take the determinant to see that, but this is maybe visually more expressive. So U has a 0 on its diagonal. Therefore, the set of vectors are what? Maybe you say it. They're not nonlinear. They're not linearly independent. So they are linearly dependent. Okay, so I mean, it was a painful way of reaching to those statements, but when we want to use it, it's not that painful, right? And it's nice that we are falling back on what we learned already. We know determinants, we know LU. Now, this is not telling us which one, right? We just know that V1, V2, V3 are linearly dependent. But which one depends on the other ones? Would be nice to know, maybe. And there's a challenge by Professor Griesel for you. Try to do it by hand for a 100 by 75 matrix. Then you will deserve an A+ in this course. Or 0, I don't know which one. In the computational course, if you pass by hand calculation, we should be fired. Okay, so next time we want to know to explicitly know which one is the dependent one.
I have a question just on like a much earlier slide. On like slide 15, it was saying like we need to develop a way to check if a vector is or not a linear combination. Like how do we do that quickly? Is this the method that we?
Yeah, we just check that.
Because like that's checking. That's where I was confused. Like it's checking if it's linearly independent or dependent. Does that mean it's also a linear combination or not?
Right. So there is an alpha that is non-zero for the homogeneous or the solution of a homogeneous system, right? Because they are linearly dependent.
Okay.
Now we're not talking about how to calculate that alpha yet. Of course, we can do that. There are examples in the book, and I'll share. There are some nice examples already available. I'll share one of them with you on Piazza. But that's besides the point of verification here. Okay. So hopefully this last example was the least terrifying part of the lecture. The calculation was quite straightforward. You can do it in Julia using what you've done already. Now, a suggestion is that do this. U times alpha equals 0. Now, we had an example, right? If U was upper triangular, we calculated alpha. For that example, alpha was 0. So try this. See if you can come up with a value. Now, the point is that if the last part is 0, alpha 3 can be any constant, right? Pick it a constant and then basically see what you get. C is not a variable. It's a constant, but it can be anything. Not to be confused with the speed of light. This is just a number. So we're going to continue next time on vector spaces. We'll wrap up chapter 7 next time, but we will see a very important matrix factorization called LDLT and a way to separate vectors. And that will allow us to do more examples on the topic, to hopefully reiterate some of these ideas. Okay, well, that's it for today. If you have any questions, maybe you can ask.